Welcome guys. So this is my final video about introduction to real analysis. So I want to talk about L2 space, and which is something I will mention and I may prove in a future videos. So basically, this is the integration of the complex function using the so start from the back measure and go to using the back measure this language and into the complex function. And the most important space are this L2 space. So I will talk about it. L2 space is important application in the quantum mechanics. Who cares? Okay. Okay, so let's say f is u plus iv, right? So usual complex, and you can say that f. So basically, I can define f is integrable, or the back integrable, even if only if u and v are the back integrable, or and f and u are measurable. F is measurable if only if u v is measurable, and also define absolute value. Okay, so yeah, so let me just write down. So let's say mu is some measure on x. Let's say on x. So I use a standard notation. So x sigma. So sigma is a sigma ring on x, and the mu is a measure, and f is complex function. So okay, so let's say we say f belongs to L of x. So this is a very bad notation. Not very bad notation. Let's say this means that you can imagine that f the absolute value defined on d mu on x is finite. So you need to sure f should be measurable and the integral must be finite. This is L space. Okay, and so most of the theorem what we previous proof works for modified complex value. Okay, so let me just quickly prove a theorem, which is maybe you need to think a little bit, which is this one. Okay, so remember previously we need to using the countably additive properties to prove this guy. In the complex analysis, we do the similar. So let's quickly go through the proof. Probably this is the 101, the first important inequality in analysis that you can always use it. If you take absolute value of something, you always pass into. Okay, so it looks very trivial. So let's say, by the way, your f need to be LU. Okay, so otherwise that this guy will be infinity. So any guy which is less or equal to infinity. So if f belongs to LU, then you can find a complex number such that its module is 1, such that C f d mu e is greater or equal to 0. Okay, you can check this is true by using your elementary junior high school or something. Okay. Okay, so you can put G equals to CF. So so this guy may be complex, right? But I can find another guy which cancel its complex part and become positive. Let's say this is u plus iv. And so now f d mu e absolute value will be what? Will be C f d mu, which is positive, which I can write as g d mu e, and write as u and u, right? Because g is now g d mu is what? Is an absolute value integral. So this guy will be real. So this guy will less or equal to right? Will less or equal to u squared v squared d mu. So this guy will be equals to this. Right. So this so final. So we prove that e integral on f integral on e d mu, the absolute value will less or equal to f d mu on e. Nice. Okay. Very simple. Okay. So now we can define L2. This space is so famous that the first time I heard about this is the first year when I was undergraduate. Okay, so let's say S is a major, the same thing. Let's say you get some measurable space, and then you can define F belongs to L2 mu. If F is measurable, sure, this is trivial, right? Because F is measurable, so you can define an integration. And if the square d mu x, which is finite. Okay, so if you are familiar with the quantum mechanics, then you know that if you get some wave function, so wave function usually is normalizable. If you work in the real numbers or whatever, it's 3-dimension, right? However, that's infinity. So in the quantum mechanics, this wave function usually defined to be some function in L2 space, right? So maybe if 1-dimensional is R, 3-dimensional is R cubed. Okay, but this L2 has some nice property that's very, very powerful. Okay, and then you can define a norm of f to be f squared d mu integral on x, take a half. Okay, so this is called the L2 norm. Sure, you can define LP norm. You can define LP norm by doing this. So you can define this in the Riemann integral, but now we define this as the back integral. So there will be something different, which is very subtle. Okay, so now this is the back integral, not Riemann integral. So my opinion is that the back integral is behave much more powerful, has some much more good properties compared to a standard Riemann integral. Okay, so sure, if you define this kind of norm, then you always have what? Cauchy schwartz. Okay, so let's say f. Let's say you have two guys. So these are very important, right? Otherwise, that I cannot talk about the norm. Okay, so let's say both are L2, and then you can prove that the FG belongs to LU. So also remember it's LU, not LU squared. Okay, and so this is d mu on x, g squared, d mu on x. Okay, so this is the Cauchy schwartz. Okay, so notice that this is finite, right? This is finite because these two are finite because they are L2. So we should prove that FG absolute value is finite. So this is LU. Okay, so this proof is very standard. So basically, you just take f plus lambda g, take your lovely norm square, and it become f squared f norm plus 2 lambda x fg d mu plus lambda squared g is norm, and take the discriminant. So discriminant need to greater or equal to 0 because this guy greater or equal to 0. So you get your answer. Okay. I mean, okay, so let me just do a computation to make it. So this is absolute. So you get 4 times fg d mu x. So b, right? B squared, sorry. B squared is equal to what? B squared that's equal to 4 times AC, right? So 4 times AC. Okay. Oh, sorry. This is I forget about square roots. Yeah. So if you take this, you get this. Okay, and you can easily use the Cauchy schwartz to prove that f plus g is equal to f plus g. This is very trivial, right? Just square it. Okay. Okay, so you can also define you can also define distance, right? But this distance is not so important. Okay. So what this theorem is very important. Continuous function forms a dense subset of L2 on AB. Okay, so let me just write down continuous function. Form a dense subset. Of L2s on AB. So what I mean is that yeah, so everybody knows about, so continuous function is always L2, right? Why? Right, because continuous function on closed and convex is always bounded. Right? So and the continuous function is always integrable. So if you square, it's still continuous, right? So it must be finite. So it must be bounded, and so it's bounded. So which is L2 square integrable. Okay. But okay, so what it means, let me just write down what it means. Right, so let's say you take some L2 square function f, let's say on AB, and then let's say somebody give you some arrow term, and then you can prove that there's a G is continuous. Let's say G is continuous on AB. So this dense means what their difference. Oh, so this setting is very, very similar as the stone wire charts. You can take about your setting, right? And then take your square and the AB, and then working on your left it's dx. Right, so now I'm talking about the usual back, right? So dx, you can take a half. And this is defined to be the norm of the f minus g. What less than epsilon. Okay, so basically, if somebody gives you a function on L2, you can find another continuous function and their difference, their norm difference is less than epsilon. Okay, so this is the what I'm trying to do. Okay, so proof. Okay, so I want to construct a sequence as a Gn, which is a continuous, and such that FGN goes to 0 as n goes to infinity, right? So then if I prove this, then somebody give you epsilon, I can pick out this Gn for large enough n. Okay, so the proof is very strange. So let's say A is a closed subset of AB. And I take K to be the characteristic function. So remember, characteristic function means that X belongs to A is 1, not belongs to A is 0. And I define T of X to be the infiniment of X minus Y for XY belongs for Y belongs to A. So somebody give you my so let's say this is A, this is Y. I will try to compute this distance. Okay. And then I can define a Gn to be 1 over 1 plus nt of X. Okay, so this is X. And then it's 1 to 2 to 3. Okay, so Gn is continuous. Why? Infiniment is continuous, right? So Gn is continuous. Gn is continuous. And the Gn of X is 1 on A. Why? Because when X is when X belongs to A, then T is 0, right? Because infiniment is 0 because it belongs to A, so that this guy is 0, right? So Gn is of X is 1 on A, and then you can easily say Gn of X approach 0 on B. So what is B? Okay, so B is just AB minus A. So AB delete A part. Okay, why? Why? Because when you go B, right? When you go B, this is closed, right? So T of X will be non-zero. So if you take n to be infinity, then this guy will be infinity. Okay. So all these are very, very simple. It's amazing that you can use this stupid thing and construct the proof. Okay, so you can prove that the Gn minus Ka, right? Because now you already have this, so we can prove this. It's a Gn squared dx. Okay, so now it made minus a Ka, right? Ka is 1. So the result will be B, the remaining is B, and you take a half. This guy goes to 0, right? Because this guy goes to 0. Okay. So you can use, I think you can use the back dominant convergence, right? Becomes 0. Okay, so proof. Very, very tricky. Okay, and remark. Let's say if f is greater or equal to 0 and f belongs to L squared. Let's say Sn is a monotone increasing function. Simple. So Sn is a non-negative and a simple function and a measurable non-negative, such that Sn approach to f. Okay. And yeah, I mean this such like this, and yeah, you can check that this f minus Sn will also be 0. Okay, so basically okay, so let me just okay, so you can just forget this part. So So remember that what we so what we have proved is what we prove is what? What we prove is that the characteristic function can be approximated by continuous function. And the simple function is the what? Simple function is the linear combination of the character, right? So simple function is also can be approximated by continuous. And also by this argument, any non-negative measurable function, you can find Sn, right? So you can go to any f belongs to L square, right? Because f belongs to L square, by previously you can prove that f belongs to L. Okay, by previously really? Sorry, I don't have this, right? So f belongs to L square, you can, which f is measurable, right? So you can find a simple function which approach to it, and then you can easily prove from here and then prove this. Okay, so the same strategy: first prove the characteristic function is true, and then prove the simple function is true, and you prove the general is true. So prove this is, I think once we prove this, the rest just follows. We just follow the simple step. Okay, so let's go to another definition. So we want to a connection with the Fourier analysis, right? So previously, I think in the chapter 8 of the routine, we talked about the Fourier analysis, which is for somebody give you also normal function and you can do however projection. Okay, so let's quickly review. Let's say you have a phi n, which is a complex value function. Let's say from x from c, and which is also measurable. So we call it also normal. If phi n bar d mu x is 0 if n not the same as n, if n equals to n. So this is usually called this. Okay, so this is called also normal if all the phi is measurable. So you can define this. Okay, so this is called also normal. And obviously phi n belongs to L squared. Okay, so this is why L2 is so strange compared to other like LP, because in L2 the also normal function already be setting to be L2, right? Because if you choose M to be, it be L2. Okay, so this is very strange that in the infinite dimension on the also normal basis is suitable for L2. Okay, so if somebody take F to be L squared, and then you can, and if let's say Cn is a projection, then we write okay, so this means that if somebody give you my by the way, this is definition, so there's no important sorry, it's important but no other non-trivial part. So if f is belongs to L2, and I can define a Cn to be, and if all the Cn is just f in the product with this phi n bar, then I will write f approximate to be Cn phi n. So I use this notation. This is the same as I use in the Fourier analysis. I never say that. I never say that these two will be equal. Okay. Okay, so the same. Okay. So the trigonometric function. So in the chapter 8, which I will prove the trigonometric function. So sorry, the trigonometric Fourier series is extended in the same way to L squared. Or basically, maybe in some cases you can even say L on, let's say, negative pi to pi. Okay. And you can easily prove that I previously proved that Bessel inequality also holds in L2 squared. Okay, so what we need to prove another theorem, which is Parseval. So previously we proved Parseval using the Fourier analysis, but in that case, which I'm talking about is a Riemann integral. So now I'm talking about the Lebesgue integral. Okay, the setting is a little bit different. So you can go back to my previous video, the previous analysis video list, and you can see there is something different. Okay, so let's write f to be Cn exponential I n x negative to infinity, where f is L squared. It's on pi, negative pi. Okay, as Sn to be the partial sum. So what I mean partial sum means that you can do k to minus n, k to minus n to n, and the ck exponential ikx. Okay, and then first part is that limit n goes to infinity, f minus Sn norm to norm will be 0. B. Yes, so this is possible. From infinity to infinity will be 1/2 pi negative pi. Okay, you can use, so previously you can prove this by using the orthogonality of this. You can prove this by orthogonality of like phi n or something, right? Because once you write f into the trigonometric function and you square, there's also orthogonality for the cosine sign. So finite or exponential or finite becomes square. So this proof, this one looks very trivial. Okay. Yeah. So actually this one is the same thing. So same technique. So I will not prove it. I only prove this one. Okay, so for epsilon greater than 0, then by previous lemma, that the continuous function is dense in L2. So there is this continuous function g, such that f norm minus f minus g norm, norm is less or equal to epsilon divided by 2. Okay, and let's suppose, and I can suppose g negative pi to be pi. This is, you can try to modify. This is not difficult. Okay, so then G extended to be periodic. Okay, so which is continuous, right? Okay, so now we need to use a previous theorem that the Stone-Weierstrass. So the Stone-Weierstrass state that continuous function on a compact set, or basically the periodic function, you can find trigonometric function which are arbitrarily close to it. Okay. So there is a trigonometric function. So this is Stone-Weierstrass on trigonometric function. So remember this. I remember what we proved this by using some very hardcore machine, and I already forget the proof. Right, but you can check it. So this is, you can check my previous video. I will post the link below if you want to check it. So there is a trigonometric function, trigonometric polynomial t of degree n, such that f minus g is less or equal to epsilon divided by 2. Okay, so now Sn minus f is less or equal to right. So you can connect these two. Okay, by remember then previously that by previously, okay, so if you choose, let's say if you choose n greater or equal to n, you can prove that this Sn, right? So previously, this Sn, right? This is partial sum. This partial sum difference minus this f is bounded by t minus f, which is less or equal to t minus, sorry, this is t, g minus t. So I'm stupid, right? Because I use this theorem on g. So t minus g plus g minus f, so which is epsilon divided by 2 plus epsilon divided by 2, which is epsilon. Okay, so proof. Yeah, this is what we previously proved in the, I think it's for analysis. I will post this part of video in below. Okay, so because it's a little bit longer. Okay, so Cauchy. So f squared f belong L2 on negative pi to pi, and if negative pi to pi, f of x is exponential negative I n x, which is 0, then f is 0. Why? Okay, so because if you have 0, right, this means that Cn is 0. So by the all the Cn is 0, which proves that the f norm is 0 by using the Parseval. Okay, now okay, so which tell you what? Okay, so let me just write down another result. So if all Cn is 0, right? So this tell you that if you have two Fourier series, so thus if two functions in L2 square U has the same, so I use L square because I use the back measure has on L2 square has the same Fourier series, then they differ. Their differences has measure 0. Or you can say that they are the same almost everywhere. Okay, almost everywhere. Okay, so now I want to talk about the convergence. And yeah, maybe I'll talk in the next video. Okay, so next video, we will try to prove the famous theorem that Reed's feature. FISCH, Reed's features. Or basically, there is a theorem very similar, exactly the same, called Reed's representation theorem. Okay, so this theorem is simple in the finite. If you're talking about linear algebra of a complex function, and it's Reed's representation theorem also showing the Stein's textbook about analysis. And the proof is somewhat difficult, so we will prove in the next videos, and we finish the complex analysis. Sorry, not complex analysis, real analysis. See you guys.